In this video, we will cover an example of Newton's law of cooling. One application of exponential decay can be applied to temperature, things either heating up or cooling down to its surrounding temperature in the air. So, for example, an object's temperature will decrease exponentially, leveling off as it approaches the surrounding air temperature. The model is called Newton's law of cooling, and it's represented by T of T equals A e to the kt plus T sub s. T sub s is going to be the ambient temperature of the room. We're going to put that in first, then we're going to substitute any given values into the continuous growth formula, and then we're going to find the parameters A and K. Once we have that, we substitute the desired time to find the temperature or the desired temperature to find the time. On the next slide, we'll have an example. So in this example, we have a cheesecake that's taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit. It's placed into a refrigerator that's 35 degrees Fahrenheit. After 10 minutes, the cheesecake has cooled to 150 degrees Fahrenheit. If we have to wait until the cheesecake has cooled to 70 degrees before we eat it, how long are we going to have to wait? So we're going to start with the model, Newton's law of cooling. T of T is A e to the kt plus T sub s. In this particular case, our T sub s is going to be 35 because that is the temperature of the refrigerator when we put that in. We have some other information. We know that T of 0, when we first take it out of the oven, it's 165 degrees. So we're going to use the ordered pair 0, 165 and plug it into our model to find A. So we're going to say 165 equals A e to the k times 0 plus 35. Of course, k e to the 0 is 1. So if I subtract 35, I get 130 is our A value. Okay, so now we have A. T of T equals 130 e to the kt plus 35. And I have some more information. I know that at 10 minutes, the temperature is going to be 150 degrees. So we'll do this same thing again. 150 equals 130 e to the 10k, plugging 10 in for the lowercase t, plus 35. Subtracting 35, I get 115. It's 130 e to the 10k. Dividing 115 over 130 is e to the 10k. And then we will convert this to logarithmic form in base e. The natural log of 115 over 130 is the exponent 10k. And then we'll divide by 10 to find our k value. So k is the natural log of 115 over 130, all divided by 10. This gives us approximately negative 0.0123. Okay, so now we have our actual model. T of T equals 130, that's our A value, e to the negative 0.0123 t plus 35. This is the model that represents the cooling of this cheesecake. If we want to know when the cheesecake will be 70 degrees, we will plug 70 in here for our T of T and solve for the time T. So we're going to subtract 35 and divide by 130. We'll convert it to natural log. And then we will divide by the negative 0.0123. So we're going to get T is the natural log of 35 over 130 divided by negative 0.0123, which is approximately 106.68. Now remember, this is in minutes, so we can say we can eat the cheesecake in 1 hour, that's 60 minutes, and 46 minutes, or 47 since it's 0.68. Okay, that concludes this video. The next video will be the logistic growth model.